Alright, so before we talk about CEM model for you, I'd like to provide you with some background knowledge about the conventional image processing techniques we can use before deep learning by the computer vision people. So in the computer vision studies, one of the very important tasks we are studying image data is to detect the edges we can identify from the input image. What is the edge? Normally in an image, the edge denoting some regions with very rapid color changes, like from blue to white, from black to yellow, and from black to blue, like these regions. We want to recognize these regions with rapid color changes in the image. Okay, so then how can we detect these edges from image data? And in this page, we show you the general process we can utilize by the conventional and computer vision people to process the image data. So normally given the input image, which is showing like this, we have a person. This person is standing by a wall. This wall has some color changes from blue to white as shown here. Right? And if you check carefully, this person is also wearing a glass. We can see that there. And this person is also wearing a dark color jacket as well, right? So when we plan to detect these edges from the input image, there will be a process. And in other words, we have a pipeline of several different operators we can use. So given the input image, the first operator we can use is called Gaussian blur operator. So this Gaussian blur operator will try to remove some noise data from the input image, like this region, right? For this kind of pixels, they are useless generally, even though we can identify something from it. So with this Gaussian blur operator, we try to remove some noise data from the input image to make this image look more blurry instead. Of course, at the same time, we're also losing some information by this operator because we lose the texture information from this image, right? And for some of the regions. And based on this Gaussian blur operator, we can further fit this image into this solver operator as well. This solver operator will try to detect some potential edges from this image and via some operations, of course. So from this image, and by fitting this one into solver operator, we can identify some potential edges, like this one will be a potential edge, this one right as well, and some other regions with larger values, there will be potential edges we can detect from them, from the image data, right? And furthermore, based on the solver operator, we can identify the edges, with another operator, it's called Canyon edge detect operator. And we can find some edges from this input image. This is a general process that we can use for processing the input image data, to detect some edges from it. So you may also wonder what are the Gaussian blur operators, solver operator, and Canyon edge detect operators. So we can provide you with some basic information for these operators we can use. And you can also gain some background knowledge before we talk about the CEM model. So first of all, what is the image blur operator and why we need to have this blur operator? So the image processing is very similar to the signal processing we have studied in some other areas or some other courses. So this image blur operator is to average out the rapid changes in the pixel intensity, which removes some outlier or noisy pixels from the input image data. It is very similar to the low pass feature we can use in the signal processing, right? And we try to remove some noise data from the image. And how to define a blur operator? In this page, we show you with the example, right? For the blur operator, we have to define some kernel matrix define the blur operator. For example, in this page, we show you with the box blur operator for image A. We denote this image as a matrix A as shown here. And what is the box blur operator we are defining? We utilize a kernel matrix like this one. This one is more like a filter, right? So inside the box blur operator, we have 1 for all the entries. And for the box blur operator, its corresponding kernel matrix is 3 times 3. And for all the elements inside the matrix, we have value 1. Then how can we apply the operator onto the image data? And we define the box blur operator as the convolution of this kernel matrix with this input image matrix like A as shown here. And the star here denoting this convolution operator we will define later. So by calculating the convolution between this kernel matrix for the box blur operator with this matrix A for the image, then we can obtain the image after the blur operator. We denote this one as G. Of course, we also have this 1/9 for the average among all the entries. And this is called the box blur operator. And you can imagine what we are doing here for this box blur operator, right? So with this operator, we try to calculate the average among a region with 3 times 3. and we sum them together, right, from this image input data, then we can calculate the average number, average value as the output for the corresponding G matrix, right? So this is what the box below operator will do. It tries to remove this outlier or noise pixel by calculating the average among the 9 pixels or 9 nearby pixels instead, right? Besides the box below operator, we can also define some other below operator, like a Gaussian below operator for the image as well. And for the Gaussian below operator, it defines this kernel matrix with this Gaussian distribution instead. Now for the Gaussian operator, we can also define a kernel matrix to be like a 3 times 3, right? And for each element inside this kernel matrix, we can calculate the value by its formula shown here, gamma xy. And this xy denoting this index of the corresponding entries for this for the kernel matrix of this Gaussian below operator. Now if we are calculating the first entry, then it will be gamma 1 1. By fitting this xy equals to 1 into this equation, we can calculate its corresponding value for the first entry. Similarly, we can also calculate the other entries inside this below operator matrix, for the kernel matrix as well. Okay, so for the Gaussian below operator, you can see it is defined based on the normal distribution with the mean value to be 0, right? However, we still have one parameter, like a sigma here denoting the standard deviation, right, for the Gaussian distribution. And on the right hand side, we also show you the performance of this Gaussian below operator with different STD or the sigma value here. Given the original input image like this one, and by assigning the sigma with different values, like sigma equals to 3 or 10, we can show you the performance of this operator. Generally, with a larger STD, then we can transform our input image into a more blurred image instead, right, as shown on the right hand side. Okay, so this is the image below operator. Besides this one, we also want to introduce the Sorbet operator as well. So what is the Sorbet operator? This operator will try to perform this 2D spatial gradient measure on an image. And it tries to emphasize some regions with high spatial frequency about the edges. And on the right hand side, we show you with the input image like this one, right? And then we try to detect some edges from it. And with the Sorbet operator, we can detect some potential edges from this input image data, right? We can see, this detection is very correct and also very precise. Then you may wonder, how can we define Sorbet operator? For the Sorbet operator, if we are starting the 2D image, right, then the Sorbet operator will define 2 kernel operators instead. The first one is called gx, the second one is called gy, right? And inside gx, we have to define one kernel matrix as shown by this one, right? This one tries to detect some rapid value changes in the x direction, in the horizontal way, right? If we identify some regions with rapid value changes from like a left to the right hand side, if so, then we can identify one vertical, edge in this region, right? So by calculating the convolution of this kernel matrix with this input image x, this data, then we can define this gx as one of these intermediate outputs. Inside this gx, we try to identify some edges in the x direction as shown here, right, by this kernel matrix. Besides this one, we also have to define this gy, this intermediate result, to detect some edges in the y direction as well. So define one kernel matrix in the y direction. This one will try to detect some rapid value changes in the y direction, like from positive to negative, right? If we can find some regions with these kinds of color changes, then we may identify one potential edge in this region, right? So by calculating the convolution between this kernel matrix with this A matrix, we can define the gy matrix as the output. So we can see that gx identifies these edges in the x direction. The gy detects some edges in the y direction. So by fusing this gx and gy together, then we can identify the edges in both the x and y direction, right? The way the operator try to fuse them is to calculate the square summation, and then we can further calculate the square root for all the entries inside the true matrix. And then we can return the result as a g. This g will identify some potential edges from it. Okay, so this is the way we try to detect some edges with a conventional operators for computer vision. So you can see from these 2 steps, we have to rely on a very important operator to define the techniques we have introduced in the slides, which is called convolution, right? And you may wonder what is a convolution and how we define the convolution, which will be discussed in the following pages instead.